We've spent a couple of lectures now talking about phase transitions. And in this lecture, we're going to talk about a theory of phase transitions due to Landau and others that describes how systems undergoing continuous phase transitions sometimes have a lot more in common than it would initially appear. To do that, we're going to first focus on the so-called Ising model, which I haven't introduced yet in these videos. So the Ising model, let me draw it in one dimension, is a theory of spins. And these spins may be pointing one of two directions. Now, this would apply also if we drew this in two dimensions. And in fact, why don't we extend this lattice to a two-dimensional one? Now, the idea is that these spins would like to be aligned. So they feel some magnetic field from each other, and that causes their magnetic moments to want to spin to become parallel. So let me draw places where we have an energy cost in this model. That is to say, places where we have nearby spins which are not aligned. I'm just going to fill in all of these places. Okay, and let me connect these dots as well. Good. So each dot represents a place where we have spins which are not aligned with each other and therefore are costing energy. Let's say that anytime two spins are not next to each other, they cost some positive energy, let's say J. And conversely, if they are aligned, they give a negative energy minus J. Now I say cost and give here because when we're at a particular temperature, when we have the system in thermal equilibrium with the thermal reservoir, then the system wants to sort of get rid or get the energy to be as low as possible. All right, great. Now there's one other element to this, which is that we could introduce a magnetic field. The spins pick up a net potential energy from the magnetic field depending on their direction. So an up spin picks up an energy. We need to talk about the magnetic moment of each of these spins. Let's say that that is mu. Okay, anyway, so an up spin picks up an energy, it's going to be mu times the magnetic field, which we'll say is H, and a downspin, and that should be minus. Let's just say that the magnetic field is up, so that if you align the spin with the magnetic field, that causes a lower potential energy. All right, anyway, a downspin picks up an energy plus UH. All right, so with these few elements, we're able to put together a model. Now, until we've done a little bit of statistical mechanics a little bit further down on in the course, we won't be able to say things specifically about the free energies of this model. And in fact, there's very little that we can say about the free energy of this model exactly in dimensions that are greater than 2. So let me start writing down some facts. And when I say free energy here, I'm talking about the Helmholtz free energy. Now, although we can't solve for the free energy, we at least do know what variables we need to characterize the state space. So the internal energy work coordinates are U, so the total energy of the system, and then M, which is the total magnetization. So M here, since each of these spins has a magnetic moment mu, if we want the total magnetic moment, we just sum over all of the spins of all of the magnetic moments of the spins. So let's say it's just mu times n up minus n down. Good. And then lastly, n, the total number of spins that we have in our system. Good. Also important, if d is greater than 1, in other words, greater than or equal to 2, we have a continuous phase transition. And we'll see how that looks in just a second. But basically, I just wanted to comment that these elements set us up for a pretty interesting situation. We could numerically try to find the Helmholtz free energy, then switch it to the Gibbs free energy. And by doing that, we might be able to find out things about the phase transition that I've described here. But if we want to be able to say anything analytically without the use of numerics, we're going to have to come up with some sort of clever approximation scheme that works near the region that we care about. So let me, on the next board, set up a phase diagram for this system, and then we'll start looking at how we might approach it. Okay, here I've set up a phase diagram that I'll fill in for the Ising model in more than one dimension. It's important to note here that we said that the internal energy work coordinates were UMN. That means F, the Helmholtz free energy, will have natural coordinates T, M, N. And the Gibbs free energy, which we'll define to be the free energy for which we've Legendre transformed M, will have coordinates that we can initially call T, eta, N. But it's in fact not too hard to show that eta turns out to be exactly H, the applied external magnetic field. This has that sort of feeling that we get when pressure, which we sort of have this natural intuition of, ends up being the Legendre conjugate variable to volume. All right, so in any case, we have F, T mu n, and G, T, H, n. So this phase diagram I'll draw in T, H space. We want to know where the phase boundary is and if there are any critical points. In fact, we know, because I've said that this is a continuous phase transition, that there must be a critical point. It's in fact very challenging to solve for this value of t where the critical point happens, although we would typically call it Tc. But it happens at 0 magnetic field. After that, we have a phase boundary that runs along the t-axis from t equals 0 to t equals Tc. All of this happening at h equals 0. So what does it mean that we have a first order phase transition here? Well, the answer is that the magnetization should change discontinuously as we change the applied magnetic field. Good. We're not going to be able to capture all of this because we can't write down F, the free energy. However, we do know that this is true from basically numerical simulation about the model itself. And perhaps also importantly, there are systems that we find in the real world that have behavior such as this. Okay, so now let's try and figure out what we can say. The answer in the Landau theory is that what we're going to do is focus our efforts on trying to describe the region only around the critical point. So let's say we're going to just focus on this region. Now above t equals Tc, we have a continuous transition. As we slide h, m will change continuously, whereas below that, m will change discontinuously. But we can at least hope that that discontinuity is relatively small as long as we stay near TC. So it makes sense to assume that m stays very close to 0 everywhere in this circle that I've drawn. Let's also update this. Wonderful. And if m is small in this circle, then it makes a lot of sense to try to Taylor expand the free energy inside of the circle. But to do that, I actually want to write down f in a slightly different way. So we have f of t m n, and I'm going to non-dimensionalize that. So look at little f, which I'll define to be capital F over n kb Tc, since Tc gives us a natural temperature scale. Okay, notice also that little f is intensive because I've divided by n. Okay, so little f is intensive and it depends on T, m, and n initially. But if it's intensive and depends on T, m, and n, we only have these two extensive variables, which means that anywhere one appears, say in a numerator, we must have the other appear in the denominator. So we know that this becomes a function f of t and m over n. And in fact, just to make our lives a little bit easier, let's also divide by the magnetization, such that this object is dimensionless. So I'm going to call this f of t and capital phi, which is just defined to be this quantity here. Notice when m is small, phi is also small, so we can Taylor expand in phi, but we've made our lives a little bit easier by having now a function of only two variables. All right, so what is the Taylor series going to look like here? We'll have f of t and phi is equal to ft, oops. It is true that it is equal to f of t and phi, but we're looking for ft0 plus partial phi of f evaluated at t and 0 times phi plus partial phi squared of f of value, oh, and I'm forgetting 1 over 2 factorial, t0 phi squared. And we're going to take this up to fourth order in this case. Oops. Okay, but there's something very important here that we should mention, and that the Landau theory is sort of predicated on. And that's that some systems will have specific symmetries that allow us to ignore certain terms in this Taylor expansion. In this case, I've already erased the figure for the Ising model here, but you can see that the system in which we have the same model but flip every single spin, so all the upspins become downspins and all the downspins become upspins, and then we flip ourselves upside down, is precisely the same physical situation as the original one. And that implies something very important. We have a symmetry that f t m n simply must equal f of t minus m n, because the physical situation for these two cases are exactly the same. All right, well, if that's true, then little f of t phi is equal to little f of t minus phi. In other words, little f is even in phi. And that evenness in phi allows us to neglect some of the terms that we see here. In particular, all of the odd terms. Good. So now we're left with only a few terms: the 0th order term, the second order term and the fourth order term. And I should put really plus O. Good. So plus higher order terms, but we're neglecting those. Okay, I'm going to clean up the board, and then we will rewrite this and see where we are. Okay, on the last board, we derived the following Taylor expansion that's approximate for little f as a function of phi when phi is relatively small. All right, well, now we're going to try to see if we can go any further with this expression. The first thing that we can do is simply rename this something like f naught of t and bring it to the other side. So now we'll be solving for f of t and phi minus f naught t, this new function that we've recentered to be at 0. By which I should say this function should have a 0 at 0. This one on the left here. And this now has only these two terms. We don't think that we're going to be able to get any more specific information without trying to figure out some stuff about f, about the coefficients here. So all we can do is really rename them. So I'm going to call this first one a of t times phi squared and b of t times phi to the fourth. But recall what's going on in this little region here. We have our first order phase transition line here, and then here's TC, so this is the t-axis. And we're looking at this region. And this means something very important. We shouldn't see any sort of discontinuity up here, but we should see a discontinuity down here. And that means that we should look at the structure of this function and see when it will permit a phase transition. And since we're focused on this h is equal to 0 line, let's think about the h is equal to 0 case. So what we want to do is think about the Legendre transform of this new function in this new case. So I guess I'll move f naught back to the other side. So we want to minimize over phi f naught of t plus a of t phi squared plus b of t phi to the fourth. Okay. Now, this is not going to affect anything, so it immediately comes out of the minimization scheme. Let's try and draw this function in two cases. Now, what we need for there to be a minimum at all is for b of t to be positive. We see that immediately. But the two cases happen when a is positive and when a is negative. So first, let's think about if a is positive, well, we have a function that is everywhere concave up, and which has its minimum at 0. And I should say a of t. All right. And then in the second case, where a of t is less than 0, instead, we have two minima that are away from 0. And I got to label my axes here. Here's phi, and here is f of t phi minus f naught of t. Okay, and same thing here. This is f of t phi minus f naught of t as a function of phi. Okay. So notice in this case that we get two minima, which should be at the same height. Again, this only works because we're Legendre transforming at h equals 0. Okay, so we have these two minima at the same height, and they're lower than the extreme point that we have at phi equals 0, which means that the system will choose one of these 2 points when we fix h. Now, this immediately brings up a good question. Which of these 2 points does the system pick when h is exactly 0? The answer is that for h slightly larger than 0, it will pick one of the points. and for h slightly smaller than 0, it will pick the other one. But this very strong reaction to small changes in h is typically called spontaneous symmetry breaking. And it turns out to be the feature of many systems that have this kind of asymmetry. I'm not going to talk too much more about it, but it's something that you would definitely see if you took a graduate level course on this same material. Wonderful. In any event, we do see that the phi that gets picked, phi star, is not phi equals 0. So what we expect is that a of t should be less than 0, exactly where we see a minimum away from 0. And that it happens when t is less than tc. That's what our numerics tell us, that we see a discontinuous jump in the magnetization as we change h a little bit. That would be jumping from one minimum to the other, and that even at 0 magnetic field, we see non-zero magnetization. On the other hand, when t is greater than tc, we must, by the symmetry, see that phi should be 0 at this point. So phi should be 0 at h equals 0. And this implies that a of t should be less than 0 when t is less than tc, and a of t should be greater than 0 for t greater than tc. Okay, so let's Taylor expand a now. So that means in the vicinity of tc, so a of t is approximately equal to a of tc plus a prime at tc times t minus tc plus higher order terms, where we see that since that when a is less than, a of t should be less than 0 when t is less than tc, and a of t should be greater than 0 when t is greater than tc, which means that this should be positive. Okay, I'm gonna, actually, I'll just write over in this space here everything that we found and summarize. So we finally found a pretty good expression for this non-dimensionalized free energy. This thing is equal to, approximately, a of tc times t minus tc times phi squared plus b of t times phi to the fourth. In the next video, we're going to check out consequences of this free energy equation and derive a little bit more that we can figure out about this Ising model system without actually doing that much work. I'll see you in the next one.